Okay, hello. So, as I'm sure anybody in the mathematics YouTube world is aware, there's this thing going on right now called MegaFavNumbers, mega favorite numbers. Mega meaning larger than 10 to the 6. Um, yeah, a lot of people have been submitting their choices and explanations. I think this is actually a really interesting thing, as obviously, if people have some favorite numbers, obviously that are much smaller. For instance, probably my favorite number, just small number, is 81, as it's the only non-trivial example of a number, the sum of the digits of a number being the same as its square root. So I like 81 for that reason. But I think it's good that the guy who organized this, James Grime, to demand that people choose numbers bigger than a million, because a lot of the time small numbers have some meaning in our lives. So for instance, 11 might be your favorite number because it was the number of your house. But of course, that doesn't really have anything to do with mathematics. Obviously, nobody's favorite number is 1,7,482,605, because that was their favorite house, that was their house number, or that was the license plate on their car. These numbers are just too big for it to be those. So when talking about these mega favorite numbers, it encourages people to think of mathematical reasons. So I thought that was a good thing that they did, to encourage a little bit more of a thoughtful mathematical discussion on it. Anyway, the number that I want to talk about today is one of the only two known sublime numbers, and I'll explain what that means in a minute. So, for those curious, there you go. That's my MegaFave number. It is 76 digits long, which I think makes it one of the larger numbers featured in MegaFave numbers so far. I mean, there have been the bigger ones, obviously. There were a few numbers that were like a few thousand digits long or something. But I think this was bigger than most of the choices that people submitted. Well, what is a sublime number? Well, we need to start by asking what a perfect number is. That's kind of that's important. So a perfect number is a number that is equal to the sum of its proper divisors. Okay. So, for instance, the divisors of 6, all the integers other than itself that divide perfectly into 6 are 1, 2, and 3. And yes, you do count the 1. And 1 plus 2 plus 3 is 6. 28 is another example. And then, via the sum given there, and you can verify for yourself that both 496 and 8,128 are both perfect numbers, if you want. Those are, you can either ask Wolfram and it'll just spit out the divisors for you, or you can have a bit of fun calculating it by hand. Either way, they're both perfect numbers. An important point about perfect numbers is something called the Euclid-Euler theorem, because it was proved independently by both Euclid and Euler, two of the greatest mathematicians ever. Euler, in my opinion, the greatest mathematician ever. That every perfect number is of this form here. So you take some integer n, and you plug it into this formula, and while you're not guaranteed to get a perfect number out of it, in fact, I believe if you plug in n equals 6, I believe that it is not perfect. 6 60, don't trust me on that, but I'm pretty sure if you plug in n equals 6, it's not perfect. Let's see, n equals 0 would be, okay, 0. N equals 1 is 2 times, so 2, that's 2 isn't perfect. Let's see, n equals 3, let's see, that would be 7 times, let's see, n equals 3 is 2 cubed minus 1 is 7, times 2 squared, 7 times 4 is perfect. 2 squared, the n equals 2 should work, right? Because that's 3 times 2, which is 6. So yeah, so 2 and 3 produce perfect numbers, but oh yeah, that's what it was. 4 does not. 4 gives you 120, and 120 is not a perfect number. So the point is, all perfect numbers can be written in this form, but not all numbers of this form are perfect numbers. It actually wasn't until, so Euler knew about, sorry, not Euler, Euclid knew about this. This was back in the ancient Greek times. But it actually wasn't until the, Euler's time, which was the 18th century or something, that it was actually proven that this formula will generate every perfect number. So, Euclid showed that all numbers of these form are perfect, but Euler showed that all perfect numbers are of this form. So, yeah, sorry, I misspoke. The thing that was known to Euclid was that any number of this form is perfect, but it wasn't until Euler that he showed every perfect number is of this form. And the proof isn't actually that hard, but we'll get to that later. The other important point is that this thing has to be a prime. So not only does it need to be able to be written in this form, if this thing here isn't a prime, it doesn't work. I actually am not sure if this thing, if this thing is a prime, this thing is definitely a perfect number. Okay, so there's a one-to-one correspondence there between Mercen primes and even perfect numbers. So for every Mercen prime, there's an even perfect number. There's exactly as many. Now notice I've said even perfect number because it's actually not known if there are any odd perfect numbers. They've checked somewhere up to like 10 to the 1500 and they haven't found any, so it's unlikely, but there's still no proof. But when I say perfect number, basically for the rest of this slideshow, I mean even perfect number. And for numbers below a certain ridiculously huge bound, like 10 to the 1500, that's true. Every perfect number under some huge limit is even, okay? So we're just gonna assume that, basically. So yeah, okay, let's move on. Now I'm going to introduce these two functions here. So the first one is tau, and the second one is sigma. So tau is basically going to tell us how many divisors a number has, and sigma is going to tell us what the sum of those divisors is. So I think it might help if we do a little example right here. Whoops. Okay, so let's do a little example. So, for instance, what would be sigma of, let's say, 48? Or actually, let's do tau first. Tau is a little simpler. So what is tau of 48? Okay, well, we need to define the divisors of 48. Now, notice I haven't said proper divisors. So when I say divisor, that means all the numbers including itself. So obviously 1 and 48 are both divisors, but 2 is also a divisor, and it has its pair, 24, 3, 16, 4, 12, 6, and 8. I think that's it. Pretty sure those are all the divisors. Hopefully I haven't missed anything. Another way of finding the divisors without basically just going through it is you can actually just prime factorize the number. So we can prime factorize 48 as, let's see, 2 to the 4th times 3, and then basically think of like all the, basically the right, like 2, 2, 2, 2, 3, and then just think about all the ways you can select 1, 2, 3, 4, or 5 numbers from the list, and you should get this list here. Anyway, so the number of divisors is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. Okay, 10 divisors. And sigma of 48 is the sum of these guys. So 1 plus 2 plus 3 plus 4 is 10. 16. 16 plus 8 is 24. 24 plus 12 is 36. 50, 74, and then that would be, let's see, 114, 122. I believe it should be 122. Let's just double check that. So 1 plus 2, so that's 6, 10, 16, plus 20, plus 40, plus 48 is 88, plus 36. It should be, I misspoke, 124. 124. Not 122, I believe. I'm not the best at mental math. Let's see, 88, 108. Yeah, 124 I think is correct. Okay, correct me if I'm wrong. I don't really want to go through the process of double checking this right now. Whoops. So yeah, so that's an introduction to sigma and tau, and they're important number theoretic functions. Now, a good definition of perfect is basically n is perfect if sigma of n is 2n. Okay, what does that mean? Well, I thought the sum of the divisors is supposed to be the number itself, not twice the number. Well, yes, the sum of the proper divisors needs to be the number, but if you include the number of itself, that's just going to double the total, right? Because the sum of the proper divisors is the number itself, add the number itself, and you get twice the number. Okay, so sigma of n, 2n, if n is perfect. Okay, now, what is a sublime number? So a number is sublime if both the number of divisors and the sum of its divisors are both perfect, but the number doesn't actually have to be perfect itself. Okay? So, in the terms that we established on this previous slide here, n is perfect if sigma of n is 2 sigma of n. In other words, sigma of n is perfect, and sigma of tau of n is 2 tau of n. In other words, tau is perfect. So example, 12 is sublime. So these are the divisors of 12, okay? And we can see that 1, 2, 3, 4, 5, 6, there's 6 of them, and we established back here that 6 is perfect, okay? And the sum of its divisors is 28, which we also established to be a perfect number. Okay, but can we find any other ones? So you might try checking, and an interesting point is that if a number is sublime, it definitely cannot be prime or square. Okay, why is that? So let's see if we can prove that. So a sublime number is neither prime nor square. Is neither prime nor square. Okay, so if it's prime, okay, then, so if it's prime p, let it be p, okay, then sigma of p is just 1 plus p, right? Because the only divisors of a prime are 1 and itself. The sum of those divisors is 1 plus p, and there's no way that 1 plus p can be 2p unless p is 1, but as we know, 1 is not a prime. So it definitely can't be prime, so we've gotten that. But it can't be square either. If square S, call it S, okay, then tau of S is odd, right? Square numbers always have a odd number of divisors, okay? Why is that? Well, every non-square number has an even number of divisors. Take 24, for instance. Okay, its divisors are 1, 2, 3, 4, 6, 12, and 24. Whoops, 24. Every divisor, okay, has like a buddy. So 1 is buddies with 24, right? Because that's the one that gives you 24 when you multiply them. 2 is buddies with 12. 3 is buddies with 6. Oh, sorry, 3 is buddies with, oh, I forgot 8. Whoops. I forgot 8. 3, 6, 8, 12, 24. 3 is buddies with 8. 4 is buddies with 6. But if a number is square, okay, take 100, for instance. Its divisors are 1, 2, 4, 5, 10, 20, 25, 50, and 100. If a number is square, then, okay, 1 is buddies with 100, 2 is buddies with 50, 4 is buddies with 25, 5 is buddies with 20, but 10 is its own buddy, right? 10 doesn't have a pair. In a non-square number, every divisor, okay, has a pair. So you can split the divisors of any non-square number into two groups. It's even. But with a square, you have an odd one out. The square root doesn't have a buddy because it's its own buddy. So you can't split it into two groups. In other words, it's odd. And we're assuming that there are no odd perfect numbers. So tau of S is odd means tau of S is not perfect to a reasonable degree of certainty. Okay? So square numbers can't be sublime under a very, very large bound, right? Because the number of divisors, even in a huge number, is much smaller. For instance, the number of divisors of 100 is only, 5, 6, 7, 8, 9. It's roughly a tenth the size of the number. So we know that there are no odd perfect numbers under 10 to the 1500, which means that there are definitely no sublime numbers under like 10 to the 1000 or something. There are no square sublime numbers under like 10 to the 1000 or something. Okay, so we've established those facts. Those are just some neat facts. Okay, so we want to see if we can. We want to see if we can find any other sublime numbers. Okay, so the first things that we need to. So basically, what we're going to do is we're going to see if we can construct a number such that sigma of n is 2 sigma of n, and sigma of tau of n is 2 tau of n. Okay? We're going to see if we can construct those numbers. I'm just going to take a sip of coffee. So the first thing that we're going to establish is that sigma and tau of n are both known as weakly multiplicative. This is a common buzzword in number theory. Weakly multiplicative. Multiplicative and weakly multiplicative are buzzwords. So basically, tau of AB is tau of A, tau of B, if A and B are co-prime. In a sense, you can break it up. You can, the whole is the same as the sum of the parts. And the same is true for sigma. Okay, so I've just stated that, but let's see if we can figure out a proof of that. Okay, so we'll start with sigma, actually. We'll start with the sigma function. Okay, so conjecture. Okay, conjecture. Sigma of AB equals sigma of A, sigma of B, if A, B are co-prime. And just for those who don't know, what I mean by co-prime is that they share no divisors. So you can list out other than 1. They share no divisors other than 1. So you can list out all the divisors of both numbers, and the only thing that they'll have in common is 1. Okay. So let's see if we can figure out a proof of that. So I'm actually going to use capital letters. So I'll have like A and B, and you'll see why in a second. So I'm going to list out the divisors of A. So the divisors of A, I'm going to say are 1, A1, A2, dot, 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 AN. Okay? And the divisors of B are 1, B1, B2, all the way up to Bn. Okay. So what can I say about this? Well, the interesting point is that whenever you basically pair up a divisor of A, let's use a different color. Let's use green. Whenever you pick a divisor of A, say A2, and you pair it up with a divisor of B, B1 say, you always get a divisor of AB. So A2, B1 is a divisor of AB. Okay? So why is this? Okay? Well, basically, if you take two co-prime numbers, let's say 16 and 25, right? They're co-prime. 25. Okay, let's list their divisors. 1, 2, and 16, right? 4 and 16. Okay, and then, oh, they're actually both square numbers. Maybe I shouldn't use square numbers as they get a little wonky. So let's pick 32 and 15 instead. Let's do that. I mean, it works with square numbers, but there were the issues with square numbers I mentioned before. So let's pick 32 and 15. So 32, 1, 2, 4, 8, 16, 32. Okay, and 15 is 1, 3, 5, 15. All right. If I match up any of these numbers, it's gonna be a divisor of the other thing. And why is that? Okay. Well, the prime, when you take the product of these numbers, the prime factorization of the product will be the product of the prime factorizations of the two numbers, right? Because prime factorizations are unique. Okay. If I prime factorize 32, that's just 2 to the 5th. Okay, 2 to the 5th. And if I prime factorize 15, which is 3 times 5, like this, okay, then the prime factorization of the product, 32 times 15, is equal to 2 to the 5th times 3 times 5. Okay, and now you have these list of prime factors that I showed before, and basically any group, okay, any subset of this is actually known as a multiset. There are 5 2s, 1 3, and 1 5. Any sub-multiset of these numbers here is going to be a divisor of the other number, okay? So, well, obviously 3 times 5 is a divisor, but we already had that because that's one of the numbers we start with. That's just 15. And obviously any number of the 2's is going to be a divisor because it was a divisor of one of the numbers we started with before. But we can actually pair up. We can, for instance, take 2 squared times 3. 2 squared is just 4. That was a divisor of 32. Right? That's also a divisor, right? Because we know that 2 squared times 3 times 2 cubed times 5 equals 32 times 15. All I've done is broken up the prime factorization. This guy right here is an integer. This guy right here is an integer. So this guy on the left is a divisor, right? So you can always match up any of the divisors in 2 co-prime numbers, and you'll get a divisor of the product, okay? Now, it's important to note that this isn't true. Let's see if we can just erase all this here. Get rid of all this, get rid of all this. Give me a moment here. This little editor that I use isn't super sophisticated, so you have to like manually erase stuff. Maybe it'd be easier if I use my mouse rather than my pen. There we go. Okay. If A and B weren't co-prime, if A and B weren't co-prime, let's say we had 50 and 20, okay, that's 1, 2, 5, 25, 10, 50, and this is 1, 2, 4, 5, 10, 20. Notice that I can't necessarily match up things, right? Because I might get something that's already there. For instance, if I match this 2 to this 2, well, I already have a 4, right? So, you know, it doesn't, you'll get a divisor, but it won't be like, it won't be a one-to-one pairing. You're essentially going to be over counting. Sometimes it glitches out like that. Give me a second. I just got to reopen this. There we go. So you will get a divisor, but it might not be. In fact, you might not always get a divisor, because notice you can match up 25 to 4. You can match up 25 to 4, and that's not a divisor of 50 times. Or sorry, it is. Excuse me. I'm just talking nonsense here. So you can match up divisors. But they won't necessarily, it won't be a one-to-one count, okay? But the important point is that by matching up the divisors of A and B, if they're co-prime, you'll not only get all the divisors of A, B, you'll get all of them exactly once, okay? So what we're going to do here is we're going to say, okay, well, we start with 1, all right? We start with 1. I'll just write this again. So 1, A1, A2, AN, and then 1, B1, B2, BN, okay? So I'm going to start with 1, all right? So 1... we can match up 1 to 1, okay, that's obvious. We can also match up 1 to B1 and 1 to B2 and etc. Okay, and we can do the same for A1, right? So we can match up A1 to 1 and to B1 and to B2, etc. And I'll just illustrate one more time. A2 we can match up to 1 and to B1 and to B2 and etc. And the important point is that if I write out the list 1, B1, Bn for the first matching, and then A1, A1B1, A1B2, dot, 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 and then A2, A2B1, A2B2. The important point is, if I keep doing this, I'll get all the divisors of AB, but more importantly, I'll get all of them only once. Okay? I'll get every single one of them only once. So what have I done here? I've taken 1 and matched it up to all these guys. A1 matched it up to all these guys. So what we can do is we can actually factor out these expressions here, right? So we have here all the divisors of AB. We had 1, A1, AN. We had 1, sorry, what did we have here? We had, right, A1. We had A1, A1, B1, A1, BN, okay, and then A2, A2, B1, A2, BN. We can actually factor these out, right? So this stays the same, so 1, A1, AN, and then this one is A1 times 1, B1, Bn, and then this is A2, draw a line here, A2 times 1, B1, Bn, okay? So I've just factored these guys out. These are all the divisors right here, and this obviously, goes on. And if we add these guys together, this is just 1 times, I'll just write B with an underline, for short, okay, to signify all the divisors of Bn. So we have A, underline, these are all the divisors of capital A, plus A1, B, plus A2, B, right, and you can think of this as A times 1, okay, A times 1, plus A1 times B, plus A2 times B, plus A3 times B, underline, dot, 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 AN, B. But we can see here that this is just, this is just the product of the sums of the divisors shown before. Because I've taken all of the, all of the A's and multiplied them by the entire list of the divisors in B. Oh, sorry, those shouldn't be A, those should be B's. That's where I was getting the confusion from. These should be B's. Sorry, B, that should be B. Yeah, now that makes more sense. B, right? So I can factor out the B underline from this, so B underline, and then we just get 1 plus A1 plus A2, plus AN. And this B underline is the sum of the divisors in B. This 1 plus etc. is the sum of the divisors in A. So the sum of the divisors in the product of coprime integers is the same as the product of the sums of the divisors. So, okay, so we've shown that the sigma function is weakly multiplicative. What about the tau function? This one is a little easier, I think. Okay, but we have to start with this assumption. Okay, so conjecture. Tau of AB equals tau of A tau of b if A, B are coprime. So we're going to assume that A is equal to P to the N and B equals Q to the M, where P, Q are primes. Now you might think, oh, this isn't general. Now we're only focusing on powers of primes for A and B. Well, okay, but if we have an A or a B that isn't a pure power of a prime, we can just, as I said before, we can just prime factorize them and then focus on the individual components. So if we can prove the results for a prime to a power, then we can just build up on that to get it for any general number. Okay, so what are the divisors of A? Well, 1 is a divisor, so is P squared, and all the way up to P to the N. Okay, and the divisors of B are 1, Q squared, all the way up to Q to the M. Okay, now, as I said before, the prime factorization of AB will simply be P to the N, Q to the M, right? So we can just take any one of these divisors and pair it up with another guy, and we'll get a divisor of AB, right? The prime factors of AB expanded out are like P, P, dot, 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 P, where this is N times, and then Q, Q, dot, 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 Q, where this is M times. And we can just take any number of these P's and any number of these Q's and just combine them together, and we'll get a divisor of AB. And the important thing, as mentioned before, is that since they're co-prime, because both of these are prime numbers, so they're A and B are obviously co-prime, then we can always, the list will always just contain every divisor once, okay? So the argument is basically the same, and, you know, we just get the same thing before, so the number of divisors of a product of two coprime integers is the same as the product of the number of divisors of each. Okay, so hopefully that was clear enough. I know that was a bit of a long, parlay into some proofs of these things, but it's important to nail down these sorts of things. So now that we know this, we can take any number. If we want to compute the sum of the divisors or number of divisors of any number, we prime factorize it first. So here the pj's are primes and aj's are natural numbers that are just exponents. So we have n as this product here. This looks really complicated, but it basically just means we can prime factorize any number. For instance, you know, we can take 30, and we can just write this as 2 times 3 times 5. Okay, that's actually not that interesting because all the powers are 1. But we could take, for instance, 48 again. We can do 48 again. Is equal to 2 to the 4th times 3. So this could be, say, P1. This could be, say, P2. And we have that this is just P1 to the 4 times P2. Or we could even call this A1 and call 1 A2. P1 to the A2 to the A1 times P2 to the A2. So, and obviously we can have as many primes with any powers that we want. Okay, so that's the general prime factorization of a number. But all of these primes, all primes are co-prime to each other. So the tau of this product is the product of the taus. Okay, and the sigma of this product is the product of the sigmas. Okay, so if we can figure out what this tau of pj to the aj is, we can construct what tau of n is. Okay, so we have these formulas here that I'll prove in just a second. So tau of p to the k is 1 plus k, and sigma of p to the k is this thing here, which I claim is equal to this formula here. Okay, so let's see if we can nail down a proof for that. Okay, so tau of p to the k is equal to 1 plus k is the thing that I claim. Okay, why is this? Okay, so p to the k. What are the divisors of this number? As I said before, 1 is a divisor, so is p squared, and all the way up to p to the k. Whoops, not the l, to the k. All of these guys are divisors. Now, we have 1, 2, 3, all these powers of p and k, so there are k here, and then there's 1. So, therefore, the sum of these guys is just 1 plus k. There we go. That's a pretty simple proof. Yeah, it's just a very simple counting argument. Okay. Now, the next one is a little trickier. Sigma of p to the k is equal to p to the k plus 1 minus 1 over p minus 1. Why is that? Well, again, the divisors of this number are 1, p squared, dot, 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 pk, and we add all these guys up. So the sum of these guys is just sum. Wow, that's a horrible summation sign. Let's see if I can... That's a bit better. I equals 1 to k of pi. Or sorry, p to the I. Okay. And this is a... Sorry, not I equals 1. It should be I equals 0, right? Because we want to include 1. I'll just erase that and correct that. Whoops. I equals 0. So, and this is actually a very well-known sum. This is a geometric series, okay? And the formula for the partial sums of a geometric series, right, is this guy right here, right? So what I'm saying is these are all divisors of p to the k. Add these guys up, 1 plus p squared plus dot, 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 p to the k is equal to p to the k plus 1 minus 1 over p minus 1. Most people are pretty familiar with geometric series and won't have a problem with this, but if this is unclear, I will link the Wikipedia page to geometric series in the description. Give it a read. They explain it really well. I don't really want to go into it now. It's a little too much of a tangent. But that's all I'm going to say. So now we know, what these guys are, right? Pj is just some prime, aj is just some power. We can think of that as p to the k, okay? And basically, tau of n is tau of this product, which is the product of the taus, and aj, k, it's the power here, so it's the product of the 1 plus aj's. And similarly, we get the product pj to the aj plus 1 over p sub j minus 1. Okay, so now we know how to compute the number of divisors and the sum of the divisors of any number. We just have to prime factorize it first, and then it's easy. So, what conditions need to be met in order for sigma of n to be perfect? So what we're going to do is we're going to say, so we want n to be a sublime number. So we're going to split this into two parts. So remember we had that sigma of n needs to be perfect. Sorry, well, not sigma. sigma of n needs to be perfect and tau of n needs to be perfect. Or more precisely, sigma of n is 2n and sigma of tau of n is 2 tau of n. Okay? So we're gonna treat these criterion separately. We're gonna do this one first and then this one. Okay? So let's go for it. So let's do sigma first. So what conditions need to be met in order for sigma to be perfect? So we're going to start with n, our number that we want to be sublime, or at least to have a perfect sum of divisors. And we're going to separate it into its odd and its even prime factors. There's only one even prime number, that's 2. Okay, so we can think of this as P1, which we'll just call 2. Okay, 2. That's the first prime. And if n was odd, k, of course, would be 0. But remember we said that there are basically no odd sublime numbers. At least not, beneath some ridiculously huge bound. Okay, so k is greater than or equal to 1. But theoretically speaking, if n was odd, then this k would just be 0. Okay, so now sigma of n is going to be this thing here. Why is that? Well, sigma, okay, let's write this out on our paper. Clear the page. So we have, we want to know what is sigma of 2 to the k times p2 to the a2, p3 to the a3, m to the am. Okay? Well, as we said before, we can just separate this, right? All of these guys are prime, so they're all co-prime. This is just sigma of 2 to the k times sigma of p2 to the a2 ... pm am. But again, all of these guys are co-prime, so we can separate it again. So we have sigma of 2 to the k times sigma, wow, that's a horrible sigma, sigma p2 to the a2 ... sigma of pm to the am. And we developed a formula for the sigma function, and we can just apply it here. So this is just some prime factorized number, and we can get the formula that I showed right here. We can just use that, starting at j equals 2. And then this guy, it's just going to be 2 to the k plus 1 minus 1 over 2 minus 1. 2 minus 1. 1 is just 1. So this is 2 to the k plus 1 minus 1. Okay. So we have that sigma of this guy right here is 2 to the k plus 1 minus 1 times this product before, which is basically the same as what we had before, just starting at j equals 2. Okay, now, because of the Euclid-Euler theorem, in order for sigma of n to be perfect, it must be of this form, with r being some integer. I know I had it written before in a slightly different way. I had n, or r, whatever you want to call it, r in here and then r minus 1 outside. But if we just make the substitution like r equals n minus 1, then this guy is just r plus 1, and then this one is just r. So that's why I get this right here. They're the same thing, just written in a slightly different way. Okay. Therefore, what we're going to end up with is that this product has to be some power of 2. Okay. All I've done is, can I collapse that somehow? Can I collapse this guy? Maybe if I just stop moving my mouse. Yeah. So we have, basically all I've done is I've taken this product here, right, and I've just re-expanded it out. Okay, instead of the compactified geometric sum formula, I've just re-expanded it out because it's going to make it a little easier to work with. Okay, so all of these guys, that product needs to be some power of 2, because the 2 to the r plus 1 minus 1 we actually already have up here. Well, it's k in this case, but you get the idea. We already have this guy. If this whole thing needs to be equal to something of this form, we already have this chunk right here. So the rest of it, this part, which I've just re-expanded, needs to be equal to 2 to the k. Okay, so let's examine the implications of that. So basically, yeah, so all I've done is I've taken this product here, and instead of with the product symbol, I've just used dots. So this thing needs to be equal to 2 to the k. Okay, so we can take any one of these little chunks, so any of the a's, it could be a2, a3, a4, in general, aj, and that has to be equal to some power of 2 to the kj. So this could be like 2, this one here could be like 2 to the 5th, and then some of the ones in the middle could be 2 cubed, whatever. And then they all need to multiply up to be 2 to the k. Okay, but why do they all need to be powers of 2? Well, it's because, as I said before, the prime factorization of both sides of the equation need to be the same. If any of these guys right here weren't powers of 2, i.e. they contained an odd prime in their prime factorization, then this thing over here wouldn't be a power of 2. So what I'm saying here, if two numbers are equal, their prime factorizations must be equal, since prime factorizations are unique. Furthermore, the prime factorization of the product of two numbers is the same as the product of the prime factorizations. Therefore, the prime factorizations of each of these chunks here can have no odd primes. In other words, all of them are powers of 2. Okay? Therefore, we can take any chunk in here and say that it must be some power of 2. Kj, and all of these kj's, k1 or k2, k3, whatever, all of them add together to k, because we have, you know, if this was like 2 to the 5th and we had like 3 things here, then we'd have like 2 to the 1 times 2 squared times another 2 squared. It needs to, the 1 plus 2 needs to be equal to 5. All of these kj's needs to add up to this k on the right hand side, okay, for it to be equal. Okay, so let's focus on one of those in particular. So let's forget the subscripts, and let's just say that one of these powers that it stops at is d equals to some 2 to the r. Okay, now, both sides of this equation need to be even. This is an even number. This needs to be an even number. Okay, for this whole thing to be an even number, forgetting the 1, this thing needs to be odd. Okay, and, well, how many terms are there? Well, there are d terms here, okay? If d is an even number, then, well, the first thing to notice is that all of these p's are odd primes, and an odd prime to any power, any odd number raised to any power is always an odd number. So all of these guys, p squared, etc., all of them are odd numbers, okay? And if d is even, then you would have an even number of odd numbers, and we know that even times odd is even, so we would have an even number plus 1 would be an odd number. We can't have that. So this whole thing here needs to be an odd number, which means there needs to be an odd number of summons, which means that d needs to be an odd number. Okay, now a little bit of algebra. I won't go into the details here. It's not that hard to verify that this thing here is equal to this thing if d is odd. And I'm using d prime as d over 2, basically. So this is 2d over 2, so it's the same thing. The point is, a little bit of algebra can show that this is the case. I'm not going to get into it. It's not too difficult, but it does take a bit of time. Okay, so basically now we have this product here. is again an even number. Well, we know this is an odd number, so 1 plus p, 1 plus an odd number, this is an even number, okay? Both of these guys, this is a power of 2, okay? This is a power of 2, right? Because, or at least this is even, but it is also a power of 2, because it can't contain any odd primes in the factorization. It's the same argument as here. If both sides are powers of 2, there can't be any odd primes in the factorization. So this needs to be a power of 2. This needs to be a power of 2. So this guy right here definitely needs to be even, okay? And a similar argument shows that d prime needs to be odd as well, okay, in order for this to be a even number, okay? And if d prime is odd, more algebra, again, I'm not going to get into it, but it is the case, we can factorize this as this thing here, if I can stop moving my mouse. Oh, maybe I can use the pointer. There we go. That's better. Maybe it'll actually close now. Nope, it's still, okay, never mind. I hope you can see this here. If this thing is an odd number, we can factorize as below, okay? I hope, I don't really want to get into it, but this is the case. And the same argument applies as before. All of these sums here need to be powers of 2, okay? All of these things here need to be powers of 2, otherwise there would be an odd prime in the factorization, and it wouldn't be a pure power of 2. So, 1 plus p needs to be a power of 2. Call it 2 to the q, and then p is 2 to the q minus 1. But we have a problem. If p is 2 to the q minus 1, then 1 plus p squared can't be a power of 2, because we get 1 plus this thing squared, and you can do out the expansion, and then factor out a 2, and you get a 2, okay, that's an even number, but then you get an even number minus an even number, that's an even number, plus 1 is an odd number. This right here is an odd number. So this whole thing can't be a power of 2 because it has an odd prime in the factorization. That's a problem. So how do we fix this? So the 1 plus p squared and any of those subsequent things, if you kept expanding that previous thing, they can't be there, okay? Otherwise, we would run into a contradiction. So in essence, all of this 1p squared, p, all of this stuff can't be there. It can only be 1 plus p. And as we said before, p is if we say 1 plus p is a power of 2, we get p is 2q minus 1 as a prime, and these primes have a special name. They're called Mercen primes. A power of 2 minus 1 that is a prime is called a Mercen prime. So what we've shown is that n needs to be some power of 2 multiplied by a product of Mercen primes. Cool. So what have we just done? So we've shown that in order for sigma of n to be perfect, n needs to be of this form. A power of 2 multiplied by a product of Mercen primes. Okay, and now, starting from this form, we can actually compute what the sum of the divisors is. And sigma of 2k, this was the product here, and now I'm taking its sum of divisors. We get a very similar thing as to before. Sigma of 2k is 2 to the k plus 1 minus 1. And then the sigmas of each of these guys, well, all of these guys are prime, right? All of these guys in here are primes. So the sigma of a prime is just the prime plus 1, and 2 to the alpha sub j minus 1 plus 1 is just 2 to the alpha sub j. So now we get sigma of n is equal to 2 to the k plus 1 minus 1 times 2 to the alpha 1 plus alpha 2 plus etc. And again, in order to be perfect, it must be of this form. Now we already have the 2 to the r plus 1, or k plus 1, in this case right here. So we must have that this thing needs to be r2 to the k. So alpha 1 plus alpha 2 plus etc. needs to be equal to k, written more compactly in summation notation. And the extra condition that 2 to the k plus 1 minus 1 must be a prime. Remember, we required that this thing be a prime in order for it to be a perfect number. So, cool. These are the conditions that we need to meet in order for sigma to be perfect. What about tau? Well, now that we've established the conditions for sigma to be perfect, tau actually follows quite quickly. So we have n is this thing here, where I'm just using pj for short to indicate Mercen primes. And we can make use of the multiplicative property of the tau function. It's basically just the products of the powers plus 1. So k plus 1 times, well, all of the powers of these Mercen primes is just 1, as we stated before. So you get k plus 1 times 1 plus 1 times 1 plus 1 times 1 plus 1, and there are m of them. So we get k plus 1 times 2 to the m. Now, in order for tau of n to be perfect, once again, it must be of this 2 to the r times 2 to the r minus 1 form. And we already have this 2 to the m, or r in this case, right here. Okay, so we need k plus 1 is equal to 2 to the m plus 1 minus 1. This also implies now that m is the base 2 logarithm of k plus 2 minus 1. And 2 to the m plus 1 minus 1 must be a prime, okay, as we stated before. Okay, so remember that we had that, I think we showed that, yeah, so 2 to the k plus 1 minus 1 is a prime, okay, a Mercen prime in particular. Whoops, but k plus 1 is actually a Mercen prime in itself. So we combine these conditions, call a number e a Mercen prime exponent if the number 2 to the e minus 1 is prime. We're searching for a Mercen prime, m, that is also a Mercen prime exponent. So m is a Mercen prime, and 2 to the m minus 1 is also a Mercen prime. And it needs to meet the condition, this m equals base 2 logarithm of k plus 1 minus 1. Essentially, the number of primes here is this number right here. It needs to be able to be the number m minus 1, right? We had k here, which is m minus 1, okay? It needs to be able to be written as the sum of exactly base 2 logarithm of m plus 1 minus 1 Mercen prime exponents. The only known, there are only 4 known Mercen primes that are also Mercen prime exponents are these guys right here. And we get the 12 from the fact that, 3 minus 1, which is 2, can be written as exactly log base 2 of 3 plus 1. Log base 2 of 4 is just 2, minus 1 is just 1. 3 minus 1, which is 2, can be written as the sum of exactly 1 Mercen prime exponents, namely 2. Okay, you can try 7 and try 31, or 6 and 30, but they don't work. Okay, this is actually a typo. That should be 126. That should be 126. Whoops. View percent. 127 minus 1 can be written as the sum of exactly 6, which is log base 2 of 128 minus 1. The log base 2 of 128 is 7, minus 1 is 6. It can be written as exactly the sum of 6 Mercen prime exponents. Therefore, we can plug this into the formula we found. We get 2 to the 126 times 2 to the 61 minus 1 times 2 to the 31 minus 1 all the way down, and you can actually do the math out, and you get this huge number out of it, and this is a sublime number. And this is the only other known sublime number other than 12. This is the only one that is known. Yeah, and I just find this amazing. I actually looked on OEIS, the Online Encyclopedia of Integer Sequences, and this jump in the list, it has list of sublime numbers, and it's only too long. It goes 12 and then this number. I believe in terms of the factor, the ratio between the second term and the first term, this is one of the fastest growing lists on OEIS. I did actually manage to find one that was bigger. It was like primes of the form k factorial over 9 plus 1, and it starts with like 4,000 something, and then it jumps up to like a 90-digit number. So that technically is a bigger jump in terms of factor, and in terms of absolute size as well. But the ratio of this number to 12 is essentially about 10 to the 75. So this is one of the biggest jumps between the first term and the second term in an OEIS list, I think, on the entire website. Even things like Rubik's Cube permutations, that goes from 1 to like 300 million or something, that's nothing compared to this. So this is one of the rarest like types of numbers, like well-documented types of numbers. So yeah, I thought this was just a little interesting thing to do. So this is my mega favorite number. I hope you enjoyed watching, and yeah, thanks. And post your own mega favorite number. So thanks for watching. Bye.